Hello, my name is Matthew Anderson. This is my lab report one for Physics 2211. So the first lab topic was analysis of modeled versus observed motion of an object moving at constant speed in one direction using tracker. The goal was to observe the momentum principle, also known as Newton's second law, which is, in an isolated system, two objects that collide have the same momentum before and after said collision, also known as an object's force is equal to its mass times its acceleration. And the result of this lab was that the object, in my case a rubber ball, given a shove, retains the momentum of the push and moves at a speed dependent on its mass and the force of the shove, its acceleration. So in this experiment, the system was the rubber ball. The source of its push was me, my hand. The surroundings was the whiteboard, the surface it was on, and the hooks to its side were to keep it in track, moving in one direction, uh, which output normal force as well as the whiteboard outputs normal force, and then of course there's the force of gravity. Um, the initial conditions, the ball started at position 0.0 meters with no initial velocity until I pushed it. Here it goes. Time. So Um, so here's the model which I created. As you can see, the modeled and observed outcomes are quite similar. The experimental trend line is clearly a decent fit, and the general shape of the observed pattern is y equals negative x, constant position for time graph. Um, Not exactly a fit to the model, but that's why it's a model. So as for the coding, uh, the first step was to change the object's mass and starting position. I found that my rubber ball was an inch in diameter and found the average weight of uh, a rubber ball of that size, um, and filled that in for ball.m, and then got the starting position from tracker and filled that in for um, ball.position using the first couple data sets. I was able to calculate its starting velocity after the push and fill that in as well. And then I set the delta t to 0.01 to match the small time frame of motion, which was only about 1.5 seconds. Uh, I did not match it to the frame rate since this could have worsened the predictions. Continuing with the coding, I'd fixed the Newton's second law while loop, so set the beginning to 1.4 seconds because that's how long the observation was. The while loop ends at 1.4 seconds, end of the observation time. Then I had to update the ball dot velocity and ball dot position lines to match the velocity update and position update formulas. So I had to add the net force over mass times delta t for velocity update, and had to update that position formula as well. And then importantly, had to set the net force to zero since we're modeling constant velocity in a constant direction, and delta t is not zero. The only way to get the left side of ball dot velocity and ball dot position to be zero would be to set f net to zero. Uh, no net force since it's a constant velocity. Uh, the later times could have been mispredicted, likely due to it drifting slightly in the y direction or small contact that the ball could have made with the books. So slight interactions might have been causing net force on the ball, making velocity not entirely constant at the end there. But like I said, it's not going to completely match the model. Um, if x and positive x, positive x and negative x were interchanged, the results would not significantly change. The graph would just appear as y equals x rather than y equals negative x. It would just go up this way instead. And is it possible to add the net forces? Yes, you could. Gravity and normal forces, the push by the ball on my hand and my hand on the ball, and possible push and normal force by the book and ball. And overall, the experiment successfully modeled the movement of an object with constant speed in one direction, demonstrating the momentum principle and basic usage of coding and tracker. Future repetitions could exclude the book part, but overall it was a success.